I'm Miyake from Okayama University of Science, Japan. I will give you a presentation entitled Proposal of Silent Multistage Compression Mechanism Using Cylinders and Vacuum Pumps. This is the outline of my talk. First, I will show you research background and purpose of our study. Second, I will show you vacuum pump performance, internal structure, and compression principle. Third, I will show you multi-stage compression mechanism with vacuum pumps. Fourth, I will show you efficiency investigation of multi-stage compression mechanism. Fifth, I will show you compression with typical compressors. Finally, I will give you our conclusion and future work. First of all, I will explain research background and purpose of our study. Compressors are used to operate the various processing equipment in the plant. The right pie graph shows an overall plant power consumption. The per consumption ratio of the compressor occupies 30% in whole plant. There are also the issue of large size, high cost, and large noise. Therefore, in this study, we aim to develop the compact, silent, and energy-saving compressors. However, there are three main problems to realize miniaturization. The first problem is that the electric motor becomes large. It is because the compressed air pressure is proportional to required torque. In order to operate the motor in high efficiency, relative large size motor is required. If the motor is operated with low efficiency, waste energy becomes heat and needs large size heat dissipation device. The second problem is the heat overcompression. This graph shows the ratio between compression ratio and temperature rising. We can see that the compression ratio of 6 leads to rise temperature of over 300 degrees. This temperature exceeds the safety temperature of 90 degrees for ideal rubber. The third problem is heat dissipation ability. To improve heat dissipation ability, the volume and surface area outside the compression chamber must be increased. As a result, compressor leads to large size. To solve these problems, we propose multi-stage compression system. The left figure shows conventional method. The conventional compressor compresses air from atmospheric pressure at once. Therefore, a conventional compressor becomes large size and hyper-consumption and generates higher heat. The right figure shows the proposed method, that is, multi-stage compression. By recompressing the air compressed at once, the required motor torque and heat generation can make it smaller. Therefore, the proposed multi-stage compression system can realize both sides, small power consumption and small heat generation. Next, I will show you the vacuum pump to realize multi-stage compression system. This table shows the performance of the vacuum pump applied to the proposed multi-stage compression system. Mass of the pump is right, that is 100 grams. Generated noise is silent, that is less than 60 decibels. The pump is inexpensive. This figure shows the internal structure of vacuum pump. Picture A shows a rubber-type piston and a check valve at the bottom. Suction port is like this. Air is supplied from lower side of the piston. This figure shows the eccentric rotation mechanism of the pump. Please pay attention to the right video. Compression process is carried out in the direction of rotation. This figure shows the model of the vacuum pump. In the model, the piston has a check valve. By this check valve, both suction and compression can be realized by reciprocating motion of the piston. Compression is done as follows. First, volume changes and negative pressure is occurred when the piston moves upward. After that, air is sucked into the lower chamber. Next, the air moves to the upper chamber through a check valve when the piston moves downward. After that, when the piston moves upward, the air in the upper chamber is compressed and sent to outlet. At the same time, the lower chamber sucks new air. Next, I will explain multi-stage compression mechanism with vacuum pumps. The figure shows the relation between suction air pressure and pressure amplification. We can see that the pressure amplification increases according to suction air pressure. It means that as the suction pressure increases, the mass flow rate of the suction air increases. Therefore, the pressure change also increases proportionally. Based on the principle, we propose a method of multi-application by connecting several vacuum pumps in the series. This figure shows the process of three-stage compression mechanism. The air is compressed in the previous stage. It's further compressed. This video shows transient view of pressure change using four-stage compression mechanism. The video is 16 times speed. You can see that the maximum pressure is at 520 kPa. This pressure is enough to drive typical pneumatic actuator. This graph shows the transient response of compressed pressure in each stage. Each color shows pressure in each stage. We can see that the compression ratio increases 2.8 times at the second stage, 5 times at the third stage, 6.6 times at the fourth stage, and so on. You can see that the high density air compression increases compression ratio. Next, I will explain the efficiency investigation of multi-stage compression mechanism. This figure shows the efficiency measurement system using four-stage compression mechanism. In order to measure the efficiency, we construct pressure control mechanism like a typical compressor. The pressure control mechanism consists of the four-stage compression mechanism, brought down with 260 cc, a pressure transducer, and an embedded controller. In addition, to measure its efficiency, two on valves to drive a double-acting type cylinder and a current sensor are also installed. The controller stops the pump when the pressure reaches at the upper limit and drives the pump when the pressure becomes under lower limit. The energy conversion efficiency is calculated based on comparison between both works of cylinder and compressor. In detail, as the compressor works to control in a certain range of pressure, the compressor works at a certain period while the cylinder is driving. Therefore, we can calculate its energy efficiency by comparing work of the compressor based on measured electric power and work of the cylinder based on number of repetitions in the period. The table shows result of conversion efficiency is setting pressure. In the experiment, compressed air after driving the cylinder was exhausted. You can see that the efficiency using three-stage compressor is around 8%. We can see that the efficiency in case of higher setting pressure of four-stage is extremely low. We think that it is related to leakage from pump at higher pressure. In addition, the generated noise level was about 55 decibel. It is the same as quiet office. This figure shows the circulation drive type system. As the compressor uses suction pumps, it can suck exhaust air from valves. Compared with the previous system, we use yellow mark circuit. By this method, the system can drive cylinder without exhaust. In addition, the system can control the setting pressure in a narrow range. This table shows result of circulation drive type. We can see that overall, the efficiency of the cycle system becomes 18 to 40% higher than the previous one. The maximum efficiency is 10.8%. Next, I will show you comparison with typical compressor. This is a typical reciprocate type compressor to inflate tires as a comparison target. The performance is like this. This table shows the comparison between typical and proposed compressors. We can see that size is compact as mass is 180 grams lighter than a typical compressor. This table shows conversion efficiency using typical compressor. Noise level is very large, that is 85 decibel. The noise is the same as the construction site. This table shows comparison of efficiency between typical and proposed one in same condition, that is to drive cylinder with exhaust. We can see that efficiency of the proposed compressor is improved 61% in maximum, and noise is more silent by 30 decibel. This is a comparison with the case using circulation drive type. We can see that efficiency is improved 89% in maximum compared with the typical one. However, there is a phenomenon that the efficiency is worse to the typical compressor in higher pressure. We are going to investigate it as a future work. This study can be summarized as follows. In the future, we plan to study the problem of reduced efficiency at higher pressure. This brings us to the end of the presentation. Thank you for your attention.